Okay, so this is Calculus section 3.8, Newton's method. I explained in the last video about basically what Newton's method is. It's a numerical method for approximating the solution to an equation. And actually what it does is it produces a sequence of guesses which is going to get closer and closer and closer to the correct solution. So let's say you have like some function. We're going to say, let's say we've got a function f of x. So in my little picture here, this is basically like what you saw in the last video. You could pretend this is our f of x. What we want to do is try to solve f of x equals 0. And in other words, find x-intercept. And we're just gonna, Newton's method is gonna find one of the x-intercepts. And depending on where you start the process, like what your initial guess is, you're gonna have the sequence points like converge on a different x-intercept. So let's say we want to find this x-intercept right here. We start by making an initial guess. We're going to call that initial guess x1. And the idea is, actually put a line here, but I'm going to move it over slightly. Let's say that's our x1. The idea is we're going to take that x1, find the point on the actual graph, and then we're going to find the equation of a tangent line through that point, and then find the x-intercept of that tangent line. And the x-intercept of that tangent line is going to be our next guess, x2. And then we'll repeat that process. All right, so that's what we're going to do. But the way I want to go about doing it in this video is without specifying a particular function f of x. We're going to do, we're going to use one of the most powerful tools in mathematics, which is generalization. So instead of solving some specific problem, we're going to take the problem and we're going to generalize it, which means we're going to kind of remove any specific information and look at the more general situation, which is you have a function, you want to solve f of x equals 0, let's apply this method. And so if I do it in generality, then what the solution I come up with can then be applied to any specific case without having to reproduce, go through all that work again. So basically, by doing this in generality, we get to do the hard work one time and then take our answer and apply it and skip all the hard steps for every time we actually want to solve a real problem. So let's see how this goes. Our initial guess is called x1, and what we got to do now with this x1 is get the equation of a tangent line. So we want to get tangent line at x1, and I'm going to figure out what that is. So remember, to get a tangent line, we need a point. The point on the graph right here, where we're going to make the tangent line, its x-coordinate is x1, and its y-coordinate is given by the function value, like the output of the function, because this is the graph of f of x, right? So to get the y-coordinate, I'll just take x1 and stick it into my function, and that should give me the y-coordinate. So then the slope of that tangent line is, of course, equal to the derivative of that function, f prime, evaluated at x1. So I'm just going to use these as my x and y and my slope in the equation of the tangent line. So the tangent line is going to be y minus the y-coordinate of my point equals the slope at that point times x minus the x-coordinate of my point. And there's a y and an x in this equation. Those are variables, but the x1 is going to be some specified point that you guess. So there's my tangent line equation. So now what I need to do with that is I need to find the x-intercept of that tangent line. So to find an x-intercept, you let y equal 0, and then solve for x. So y is 0. We're going to do 0 minus f of x1. So that's just negative f of x1 equals this stuff over here. And my goal is to solve for x, right? So let's divide both sides by this f prime of x1. Negative f of x1 divided by f prime of x1. And then it's going to cancel out on the right, so we just have x minus x1. And then you can add the x1 to both sides. So what this is going to give us is, and I'm going to swap the left and the right sides of the equation here. It's going to give us x equals x1 minus f of x1 over f prime. of x1. And that right there is our formula for getting the next number in the sequence. And so this number, this is the x-coordinate of the the x-intercept of the tangent line. That would become x2. All right, so your next guess, x2 would be, and this is going to rewrite this, because then the next guess after that, x3 is going to be, apply the same formula except for x2. So you would go and get that tangent line, beep, 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 and then get that x-intercept of that tangent line. So you do exactly the same thing except with a new number. So this is going to be x2 minus f of x2 over f prime of x2, and so on. x4 is going to be x3 minus f of x3 over f prime of x3. So this formula translates into what I like to call the iteration formula. It is the formula that describes the iteration we're going to do. Iteration means doing the same process over and over and over again. So like you do a process and then you take the output and plug that back into the process. It's like kind of like applying a function over and over. But in this case, we're going to be applying this formula over and over and over. And the iteration formula can be written in generality as xn plus 1 equals, which would be the n plus first number in the sequence, is the nth number in the sequence, which was the previous one, minus f of xn over f prime of xn. There we go. So we have our powerful tool. This is the heart of Newton's method right here. It's that iteration formula. So now we're going to do an example.